Okay, so let's take a look here. We got the kinematics questions. Any recommendations for one to go through?
Yeah, I have a couple.
Okay. Of the, meaning the last one? Any other than the last one to go through?
Mine's number 7. I don't know if it's the same.
This is the, yeah, 3.3.
Is everyone the same?
No.
Because you have that one really hard one.
Because I have one that I'm just like.
Okay, so which one is yours that you're having trouble with?
You know,
Can I just go to yours and look?
I think it's 7.
Okay.
it's number 7.
Okay.
Why don't none of these can?
Because those are the ones I got left there. It's like that island of misfit computers. Heck yeah, I am. What?
Okay, Peyton, this is you. Which one?
Number 7.
Number 7?
8, I think.
8.
It's one that's not answered, but it's not 10.
Oh no, this one is.
So that one right there, maybe?
Yeah.
Okay.
Oh gosh, it's embarrassing.
No, that's not
This
embarrassing.
is really awesome.
06. Okay, so the bike one. I'm gonna see if I can find.
Yeah, I know, there's a lot.
Okay.
Everyone's stressing now.
Right here. This guy, right?
Yeah.
Okay, so yeah, let's talk about this one.
No, that's not the one that.
Wasn't it? I think it was.
Yours has like reaction time.
No, it's right there.
Well, obviously that was right.
Same idea.
It would say it was just one.
Isn't the one that you're having trouble with the one with like reaction time?
Reverse, she told us.
She got that one. Oh,
She's confused.
Okay, so let's look at this. Now, even if it's the one where they're talking about the reaction time one, and that's the one with the car driving along, right? And you may or may not have gotten. I mean, there's some variability. You won't all get exactly the same. Obviously, none of you get exactly the same questions, but you may not even get the same types of questions. Yeah, I mean, there's some variation in these. But all the bases are going to be covered here, meaning you're going to get a problem that's going to deal with the same concept. And a lot of them really, a lot of them have the concept that they're getting at is that you've got this situation where there are two parts to the motion, right? The acceleration changes. Like in this one right here, for example, the bike uniformly accelerates from 0 to 15 meters per second in 4.5 seconds. Okay, so that's the acceleration is some positive value, right? Which we could calculate if we wanted to. And then it continues at that constant speed of 15 for another 3.5 seconds. So that's part 2, right? Remember we talked about how if the acceleration changes, you have to break this up into a different part, right? So it's like different scenes in a movie or sort of, right? We've got the first scene and then the second scene. So we need to come up with all of these types of questions. Our goal is to identify what it is that we're given and what it is that we're trying to find, and then use the appropriate kinematics equation for that situation, right? And we don't have any choices right now. It's going to get a little more challenging when we get into sort of the next iteration of kinematics questions, because then we have more formulas to deal with. We have more types of kinematic quantities that we're going to have to be probably involved with. And so it's just like one incremental level more difficult. But at that point, you'll also have a lot more experience and practice with it, so it may not seem. All right, I'm just going to take a picture of this. Okay, so there's the situation. Now, what information, let's break this into parts. So we'll go part 1, part 2. For part 1, what's something that we're given? Okay, so we're given, we could certainly,
Initial and final.
okay, initial and final velocity, there's something, right? So what's our initial velocity for part 1? 0. Okay, what's our final velocity for part one?
15.0.
Okay, and what else are we given?
Time.
Time. And that's 4.5. What are we trying to find? Trying to find, okay, trying to find displacement, right? We want to find overall displacement, so our goal is to find a displacement for part one and a displacement for part two, just add them up, right? So we're looking for delta D. And so what's the relationship that we're going to exploit here then? What's the formula?
Velocity times time.
Okay, so the formula we're going to use is displacement equals average velocity times time, right? That make sense? And we're trying to solve for displacement, so it's actually even already solved for the variable we're looking for. So all we have to do is plug these values in, okay? We've got time. How are we going to calculate an average velocity? Yeah, okay, add up the two values and divide by 2. And one quick point I'll make. Why is this such a key word here? Uniformly.
So that means it's
Okay, so it's accelerating at a constant rate, and so we're picking up speed at the same rate right now. It wouldn't work if, like, let's just say that we accelerated very slowly for a while at a very small rate until we got up to 14 meters per second, and then, or we got up to, let's say until we got up to halfway there, so we got to 7.5 meters per second, and then we just shot up really quickly to 15. Then we couldn't do this problem the way we are, right? Because we're going to cover a lot more ground during the first part of the story, right? The first part of the first part. If we were to accelerate from 0 to 7.5 very slowly, we're going to cover lots of ground while we're doing that. And if we just, in a really small amount of time, went from 7.5 up to 15, we wouldn't cover very much ground during that interval, right? And so it wouldn't work for us to say that the average velocity is 7.5 because we would have had the average velocity would be more complicated, right? Because it wasn't uniform. But because it's uniform, because we're changing from 0 to 15 regularly, we can just average the two. What do we get? 7.5. Okay? And so all we have to do is multiply 7.5 times 4.5 and get what if we do that? If we plug and check here, so. So we're going to get 30 plus, so it's going to be 30.375, is that right? What?
I got 33.7.
I mean 33.75, that's what should be, that's what I meant. All right, so what's that going to round to? 33.75.
34.
34. How come 34?
Should we?
Wait, why don't we round
Oh,
it
sorry,
right now?
yeah, you're right, my mistake. We're not going to round yet, are we?
Nope.
33.75, okay, hold that thought. And then for P2, what do we know for P2? Okay, so yeah, the velocity is the same the whole time, and so because it's constant, it's its own average, right? We don't really, it'd be kind of silly for us to write down initial velocity equals 15, final velocity equals 15. We don't, right, we just know that for P2, that our average velocity is 15.0, and what's the time? 3.5. So that's going to give us 52.5, right? So we'll just add up those two quantities and then round.
So how was our average velocity 15? On the end accelerator.
Because part two, here's where we've got, here's part one. And here's part two. Right? Part two, it continues at that constant speed of 15.
Oh,
right, for 3.5 seconds, okay? And so that, whatever you get, right? You add those up, round to how many sig figs? 2. Okay. All right. What else? Which one?
It would be my 7, but it's the one where the driver sees a kid standing in the road.
Okay.
Slow.
Okay. So,
How much force is exerted on that?
so this guy right here.
Yeah.
Okay. So a car's traveling at 28 meters per second when the driver sees a child standing in the road. She takes 1.4 seconds to react, then steps on the brakes and slows at a rate of 5. How do I say those units? Meters per second squared. Those are units of what? No, meters per second squared would be units of acceleration. Good. The car travels a total distance of blank meters before coming to rest. Okay, this is really the same deal, isn't it? Because now it's sort of the reverse of what we had before, though. Now the car is traveling at constant speed for part 1, right? And then it's accelerating for, we could say it's decelerating, which really in this case, if we're assuming it's traveling in the positive direction, means the acceleration is just what? Negative, right? Okay, for part 2. So we've got to fill in the same, we've got to fill in the same blanks in those equations, but we're given the information in a different way this time. So we have to interpret the information that we're given in such a way that we can still calculate an average velocity for both parts, right? Okay, so how are we going to do that? Let me grab this.
Can you explain again
Yeah, right. Because think what's the definition of acceleration? Rate of change of velocity. So change in velocity over change in time. So we're going to have units of velocity. Acceleration must be units of velocity divided by units of time. So that's a meter per second, right? And just a more compact way of saying that is a meter per second squared. Okay, does that make sense? Okay. Okay, so part 1's not going to be a big deal. I'm not so concerned about part 1. I think everybody's going to be okay with that. So what can you tell me about part 1? It is your average, right? Because it's traveling at constant speed. So part 1, average velocity equals positive 28.0. What else do we know? What else do we know for that one? Times 1.4 seconds, so we can easily find the displacement, right? Not a big deal. Okay, part 2 is a little trickier. What information are we given for part 2? Okay. So now, what's the acceleration? Negative 5.0, right? Standard units, right? What else? There's some other stuff that's given and implied.
Comes to a stop at 0. So
Okay, so the initial velocity is 28. The final velocity is 0. Okay. So then in order for us, our goal here, right, is to get an average velocity times a time, because that's how we calculate displacement, at least in this assignment. Right? Later on, we'll have a bunch of other ways to do it. Okay, average velocity is no big deal. What's that? 14. Okay, but what about the time? How are we going to get the time? How are we going to get that?
velocity divided by acceleration.
Okay, so we got to use the other, now we need the acceleration formula, right? So the acceleration formula, what is that? Well, where it comes from, remember, we know that the definition of acceleration is change in velocity over change in time, right?
So divide those. Initial velocity by the deceleration.
Well, okay, so what are we're trying to find out in this one, we're trying to solve for t, correct? Okay, so the formula that we get from this, by the way, if we multiply both sides by delta t, which is really just t, then we end up with delta v equals a t, right? So divide by a, yeah. All I gotta do is divide each side through by a, and then that allows me to solve for t. Okay, make sense? And that's my goal. I want to come up with an equation solved for the variable that I'm looking for, where that variable is isolated. So now we can just plug and chug. T equals change in velocity over acceleration. Remember, change in velocity is always going to be final velocity minus initial velocity, right? So what's our final velocity? 0 minus divided by. Okay, make sense? So that's going to give us what, 5.6? 5.6 seconds, right? Does that make sense? Okay, is that our answer? Well, not exactly. We're getting there. That just gives us another quantity to fill into our kinematic quantity list, right? Now we can put t equals 5.6 standard units, and now we can plug everything we need to up there, right? We good? Okay. All right, so how much time we got? Eight minutes. All right, so to the last one? Okay, let's talk about the last one. I don't want to tell you too, I mean, yeah, we'll talk about it. I'll give you some hints on this one. So the last one. Tell you what, you guys, I will be a receptacle for your ideas. How's that sound? All right, so a truck is stopped at a stoplight. When the light turns green, it accelerates at a rate of 3.7 meters per second squared. At the same instant, a car passes the truck going at a constant speed of 28.0 meters per second. The truck overtakes the car after traveling a distance of what? Okay, so I did give you something. I did give you a new equation on this one, though, right? Aha, okay.
Yeah, we do. No, we have time, with the, 3.5 meters per second. Yeah, with the car, right? No, the truck. But meters per second squared means that you have time. Well, technically you have time on both. Well, because the second squared is equal to time, is it not?
No, not precisely. I'm not sure where you're going with this.
Not equal in the sense of numerically, but, for other words.
Seconds times seconds.
Yeah.
So I gave you the equation, displacement equals initial velocity times time plus 1/2 acceleration times time squared, right?
Yeah.
Okay. So let's do this. Let's think about this from the perspective of the car and the truck, right? So let's deal with the truck first. What kinematic quantities do we know about the truck? It's big. Oh,
We know
okay.
acceleration. Oh wait.
Do you want me to plug them in?
Would you mind plugging it in? That'd be great, thanks.
We know acceleration.
Okay, we know acceleration of the truck, so I'm gonna call that a sub t. And what's that equal to, 3.7? Okay, what else do we know about the truck?
Oh yeah.
It stopped. It's going.
Oh, okay, so what is its initial velocity? 0. V naught sub t is 0, right? Okay, so
You could.
would you guys agree, everybody in here agree then, that I could fill in the blanks up here, I could solve for the displacement of the truck in terms of numbers and time, right? Because I know its initial velocity and I know its acceleration, right? Okay, so let's do that then. So this tells us that the displacement for the truck is equal to 0 times t, so it's just equal to 1/2 times a. So what's that gonna be, 1.885, whoops.
Because, the velocity is 0, 0.
Oh, because 0 times t is 0.
Right, because we know the initial velocity is 0, so 0 times t is 0 plus 1/2 of 3.7 is 1.85 times t squared. Okay, so there's one equation, that's useful, there's our equation for displacement of the truck. What about the car?
That's the graph. So they think intersection.
Okay, so what do we know about the car?
The car is going at constant speed.
So we look at
Okay, okay. So V bar sub car equals 28, right? So all we need for the car is just our old equation we've been using. Delta T equals average velocity times time, right?
Yeah.
So if we write that in terms of T, delta D sub C for car equals 28.0 T. Okay, this is all I'm gonna tell you. You'll tell yourself this. So what has to be equal when the car and the truck pass each other? Time, right? Because we're starting the stopwatch at the same time, right? When they pass each other the first time, agreed? What else is displacement? Because we're looking for the specific time when the displacement is the same, or vice versa, for the displacement when the time is the same. Really, all I've got here, how many variables are there in this equation right here? 2. How many variables are there in this equation? 2, right? I guess technically delta d sub t and delta d sub c look like different variables, but we're really just looking for the time when those are the same, right? So really, I could even just go in here and maybe even just erase those subscripts, right?
Just make those equal to each other.
You can, right? This goes back to kind of algebra 2 stuff, right? We're just going to solve this system by just substituting, okay? Which one do we want to substitute? Well, I would say that being as these are already both solved for delta D, that we could go back and say, okay, well let's plug like 28.0 T in right there. Whoops, I guess I erased it. So we're going to plug this in right there and then just solve for T. When we solve for T, it's a quadratic equation. We're going to get 2 solutions. What's one of them? 0, right? Because we know that their displacements are the same at time 0. We want the other T, right? And if I know what that other T is, I'd be able to plug it back in and find delta D. Right? Make sense? That's a little tricky. That's good though. All right. Turn in your Chromebooks and you have questions. Yes. Hey.
On your calculator, how do you make it so just the
Oh, I got it. Okay, so yeah, all you have to do is just make X needs to be a lot bigger. Wait, go around so you can make the window something. But you will with all
If I go to the intersect and get the sum angle, that's not the answer.
Can't you just?
Yeah, I know.
So yeah, you probably won't.
Yeah, I know. The graph looks right, but I think somehow we're checking weird.
Kind of like
Weird setting.
Oh, I got one.
On the game.
So it's like, I still have one sitting in the back of my car.
It's like, what is it?
Give it a sub bump.
All the.
probably trying to find officers here.
Like, where's the one bill?
Alrighty. So I'll just finish up the 3.3 assignment. I'm gonna do a little test tomorrow over the Moodle assignments. Okay? Moodle assignments from chapters 2 and 3. It shouldn't be a big deal. If you've done the assignments, there's probably very little studying you need to do.